Today we'll take our minds off the current political situation and talk about Mars instead. So let me put this aside here. But good, I'm glad to see that you're all turning out to vote. That's encouraging. Okay, so I'll put this, clear the question, and then we'll have a science warm-up question, and you can work on that while I go through the announcements. I'll give you a little bit of time afterwards. It's a little tricky, so you may want to wait, and I'll give you some hints. The exam was on Friday, and hopefully most of you remembered to take it. I think most people did take it. There are a few people who didn't, and hopefully it's not because they forgot, but it was a conscious choice. They're so confident in their abilities on the first exam, how they did on the first exam and how they'll do on the final. They decided to use the second exam as their drop, and some people take that risk. It is what it is. And if you now go to WebAssign down in the announcement area, I've updated the grading spreadsheet, the score to grade conversion spreadsheet. So you can grab the new copy of that, and you can enter in the scores for your first 6 homeworks and the first 2 exams, and let you know where you stand in the class. And this is actually both sections combined. I don't know if when I do the final grades, whether I'll split you out or just do it all together. I'll figure it out, but my impression is it doesn't matter. We're getting similar grades between the 2 sections. Anyway, you can download that, see where you stand in the class rank and what grade that corresponds to. If you're one of the ones who did not take the second exam or the first exam, it will probably say you have an F because it's not dropping the exam yet. You know, I dropped 1 exam or half of the final. Final counts as 2 exams, and it's not doing that drop yet. So if you want a better idea of where you stand in the class, just enter the same exam grade twice. You know, whichever exam you took, enter it twice, and that'll let you know where you stand. It is dropping your worst homework already. So now if you have a second homework that you're also not proud of and want to get rid of, again, there is the extra credit opportunity in the ebook under lesson 5 at the bottom. It's a 2-page essay that you turn in with the final, and you can get rid of another homework exam. Okay, any questions about the exam? The average was an 80, so right at the BC line, which is kind of where we need to be given the college's rules of what the average GPA should be. So there'd be a mild positive curve, but it'd be very mild in this case. Let's see, next up is homework 7, which is due on Thursday. Not our usual time, but we're decreasing the amount of times between these so we can get 7, 8, and 9 done before the end of the semester. And since it's due Thursday, I'm going to move my office hours to Tuesday this week. So no office hours on Thursday. Office hours will be on Tuesday. Same time, 2 to 3:30. And I'll be there in case you have any questions that need to be answered. I won't get through all the material today, but I'll get through most of it, probably more than halfway through Mars. And homework 7 is the terrestrial planets. So it's Mercury, it's Venus, and it's Mars. The date of the final, we'll pick that next time. And I'll send an email out with some reminders about this before next time and before the moved office hours. But since I'm giving you 24 hours to take the exam instead of the usual 3, it does not have to be during the usual scheduled time, as long as I get permission of my chair, which I did. And so that's more useful for me because I don't have to write 2 separate finals for the 2 sections. It enables me to pick a single 24-hour window for both sections to take it. I only have to write 1 final exam, which makes my life better. But I'll let you all pick the date. The first section I'll give you an array of possible opening dates, and it'll be due 24 hours later. And the first section will vote, and you'll vote, and I'll put them together. And as long as it looks reasonable, I'll get back to you all with when it will be. Okay. I think that's it for announcements. Any questions about anything? Okay. Let's take a look at this warm-up question. So I want you to order from oldest to youngest, the surfaces of these plants. Of course, all the plants formed at the same time, but some surfaces are older, some have been remade through various processes we've talked about. And so I want you to consider Mercury, the surface of Mercury, the lunar highlands, and the lunar maria. And kind of the key for doing this, I'll give you the big hint. You got to look at the density of craters. We know that the cratering was really intense in the first 500 million years. You know, we've taken rocks from the moon and dated them radiometrically, and we could tell that the cratering was really intense in the first 500 million years, and then it tapered off quickly. And so, you know, if the surface was remade at some point, it will only have the cratering from after that point in time, which will be less than if the surface was never remade since the beginning of the solar system. Anyway, I think I have a, nope, let me grab a better quality version of this picture. So I think I have it here. I'll slide that down in case you need slightly higher resolution. And then I'll shut up for, oh, I don't know, 40 seconds.
Did you do anything for Halloween, Dr. Reichert?
I do anything for Halloween? Not really. Normally we put candy out for the trick-or-treaters, but because of COVID, we decided not to do that. My son in college Zoomed in, and my bonus son came over and we watched The Mandalorian, which was pretty good. Part of it was shot in IMAX, which is not something you see often on TV, right? For movies, sure, but television, they usually don't pay for IMAX. So that was kind of cool.
Dr. Reichert, did you see how they do like the behind the scenes on that movie? How they have huge like LED backgrounds where they update the background of the movie, and it's like new technology. It's kind of cool.
No, I didn't see that on The Mandalorian.
So they have
behind the scenes.
massive high resolution LED backgrounds sometimes for the sets, and then they have the camera synced with the LED background, and when they move the camera, the background changes too for the perspective. It's kind of cool.
Oh, that's cool. Yeah, I'll look for that. All right, let's see. We got 18, 19 responses. Now, the last class, I had to put them in the breakout rooms. And so that's a possibility this time. We'll see what we got here. Maybe I need to add a few bins. Okay, so most of you picked, oh, it's kind of a tie between 1, 2, 3 and 2, 3, 1. Neither of which are correct. So it's not 1, 2, 3. It's not 2, 3, 1. Again, you really have to focus on the density of craters. So I'm going to make this really big, and you can screen capture it because I'm going to send you in the breakout rooms to discuss, and then you can revote. But the highest density cratering will be the oldest, and then the lowest density means it was renewed the most recently, so there haven't been as much craters since it was renewed. Okay. So I'm going to shrink this, and I'm going to send you into the breakout rooms. And let's see, we got about 30 of you, maybe 6 breakout rooms. Okay. I'll give you about a minute and a half to discuss. Okay, everyone's back. Go ahead and put in your new sequence. Yep, 213. That is the answer. So let's walk through that. So number 2 was the lunar highlands. If you look at these, you have the highest density of craters. We have crater upon crater upon crater upon crater. So this area has really never been resurfaced. It dates from as soon as the moon solidified, somewhere in the first 500 million years of the solar system. So about 4 to 4.5 billion years ago. The next oldest would be the surface of Mercury, and it's fairly cratered, but you can see there's spaces between the craters, the intercrater planes that we talked about. And remember, Mercury, we think what happened to it to develop its supermetallic core, it encountered a big hit or maybe a handful of smaller hits. They removed a lot of the mantle. It would have been remolten. Any cratering from before those hits would have been erased. And then this is the cratering we have afterwards, and there's less of it than the lunar highlands, so you know it's a newer surface. It was renewed more recently. Then you have the Maria, and there are craters on the Maria, but they're relatively crater-free, and they date to about 3 billion years ago. With the lunar highlands and the Maria, we brought rocks back and we dated them radiometrically. That's how we know the dates. But then for anything else in the solar system, like Mercury here, we can just look at the cratering density, and it puts it in that pattern, even though we haven't radiometric dated any of these rocks. So lunar highlands 2, Mercury 1, lunar Maria 3. That makes sense now? Okay. Yeah, it was a little bit above and beyond what we had discussed in class, not just a regurgitation of material. So wanted to make you think a little bit, and that worked out. Okay. Let's move on to Mars. And we'll get partway through this today and we'll finish it up next time. Let's start with just a few images of Mars. So this is, I can't remember if I did this last time. I don't think so. So let me pull this up. So this is Mars as imaged from the ground here on Earth. When Mars is at closest approach, when it's far away, it's really small and you can't see any features on it. But when it's at closest approach, you can see some detail. And it's at closest approach now. If you're in the lab course, you probably saw some detail. If you look carefully, you might have seen polar caps or variation in the coloration. These are pretty good images. It's almost as good as you can do from the ground without some really expensive equipment. Because again, you're looking through the atmosphere that blurs things out. But we see lighter regions, we see darker regions. Up here, we see one of the polar caps. There's also a polar cap in the south. It just depends which side is pointed towards us at the time. And this is, of course, a full sequence, so you can see a rotation. It gets better. Let's get rid of this. It gets better if we can get above the atmosphere. These are pictures of Mars taken with the Hubble Space Telescope back in 2003 when it was also at closest approach. And you can see the light regions and the dark regions in much greater detail. Here we're looking at the southern polar cap, and we'll get to these caps later today or next time, learn a little bit about them. They're kind of different from our polar caps. And of course, you can get more detail if you go into orbit, if you actually go to Mars, get up really close. So here we see such structures as the Ballast Marineris, which is a giant rift valley, a valley caused not by erosion like wind and water, but from the ground just tearing open. And we'll learn why that's the case. These dots over here are volcanoes, tremendous detail that we can get being in orbit. And of course, on many occasions, we've landed on the ground, and often with rovers that can move around and check out different terrains. So we have a wealth of data, tremendous data from the surface itself. So it's probably one of the best studied planet, other than Earth. It is the best studied planet, I think. And that's in part because we're looking to go there eventually and to colonize it. It's our best option in the solar system for creating an Earth-like environment for sustaining humans. But as we'll see, it's really not a great option. It's just the best option we have. Let's take a look at the bulk properties. Again, the mass and the radius, and the three things we can calculate from the mass and the radius. I'll just write them quickly. M over r cubed, the average density. M over r squared, the surface gravity. Square root of m over r, the escape speed. And again, if you put those in Earth units, you get everything back in Earth units. You get the average density, the surface gravity, and the escape speed as a fraction of Earth's value. So here's our table that we've seen before. And here's Mars. Mars is about half the size of Earth and about 10%, 11% of the mass. So very different from Earth. Let's calculate our three favorite things: average density, m over r cubed. And in this case, we then multiplied it by Earth's density to get it in kilograms per cubic meter. And it came out to be in the high 3000s, different from Earth in the mid 5000s. And that tells us that there's less metals here, more rock, less metal compared to the Earth and Venus and Mercury. It's very similar to the density of the moon, which is also in the 3000s. So it's a primarily rocky world, but certainly some metals mixed in. If there's pure rock, it'd be 2 to 3000. Surface gravity came out at 38%, and actually exactly the same as Mercury. So if you travel to Mercury, if you travel to Mars, your weight would be 38% the value here on Earth. So once we eventually go to Mars and start to colonize it, the people who stay long term will have to get used to that low gravity environment, and which could be challenging. Our bodies were built for 1G, not for 0.38 G. And so there could be long-term consequences for low gravity experience. And then we have escape speed. You calculate the fraction and multiply it by Earth's to get it in kilometers per second. And it comes in as 5, which is, close to Mercury's value. It's pretty low. For Earth and Venus, it's much higher. And that means it's going to be easier to lose your atmosphere because the escape speed's lower. Now, it's farther from the sun than Mercury. Mercury has the combination of really high temperatures and low escape speed. The higher the temperature and the lower the escape speed, the easier it is to lose your atmosphere. In case of Mars, you're farther from the sun, so at least they have cooler temperatures, but they still have an escape speed. It means that most of the atmosphere is lost, but not all. There's still a little bit. Okay, so those are bulk physical characteristics. And the key takeaway is Mars is a lot more like Mercury than Earth. Now, we keep looking at Mars as the future home of humanity or the next home of humanity. But in terms of bulk properties, Venus is a much closer match in terms of mass and radius and all these three things. But it has a number of really unsolvable problems. The surface temperature, 855 degrees Fahrenheit, that just won't work for us. The slow rotation, and biologically, it'd be hard for us to get used to a day being over 100 days, between the sun coming up and the sun coming up again as you experience it on the surface. Mars is better in other respects, though it doesn't match in terms of mass and radius and hence gravity and escape speed and density. And there can be consequences there that we'll have to deal with. Now, Mars is different in those ways. As we said, in these ways, it's more like Mercury. But it's like Earth in some ways. First of all, well, taken both together, the rotation and the tilt. It rotates on its axis once every 24.6 hours. So that is very Earth-like. That works with our biological clock that's been evolved over a very, very long period of time. And so we won't have to adapt very much. The days are a little bit longer, but we should be able to get used to that. In fact, we already have some people living on Mars time, not on Mars, but the people who run the rovers in the experiments on Mars, they work in shifts and they have to work on Mars time, like Mars day, Mars night. And it's okay, it's pretty close to 24 hours. They can still sleep normal amounts of time, but that extra 0.6 means their day is shifting with respect to ours. So these Mars rover control teams, for long periods of time, they're aligned with our day and can be awake when it's light out. And then for a long period of time, they're working night shift, and it slowly cycles through. The tilt of Mars is 24 degrees, which is almost identical to our 23.5 degrees. And so that means, we have similar length day, similar tilt. The similar tilt means we're going to have similar seasonal effects. So in some regards, we are, Mars is Earth-like. Now, the tilt, it does give you similar seasonal effects, but there's one more thing that is different from Earth, and that is proximity. Now, in lesson 2, I spent a lot of time emphasizing that our seasons are due to the tilt of the planet, not because our planet's closer to the sun or farther away. In the case of Mars, it's a combination of the two. The seasons are primarily due to the tilt, like here on Earth, but they're supplemented. The temperature is supplemented or detracted from because the orbit is not perfectly circular. Sometimes it is indeed closer to the sun and sometimes farther away. So here we have the sun, and here's Earth's almost perfectly circular orbit. And then we have Mars, and you can see that orbit, it's fairly circular, but it is slightly eccentric. And at closest, let me give you the range here. At closest, it's 1.38 AU from the sun, but it can be as far as 1.67 AU. And that difference here, when we're close, you're getting 45% more light, and hence more heat from the sun. And that does cause a temperature change. In fact, it's one of the homework questions. You're going to use the temperature equation and figure out how much the temperature varies from when Mars is at this distance versus that distance. And there will, there's a temperature difference. It's not the primary thing, though. The primary thing is still the tilt. It determines the seasons. But this can modify them in a peculiar way. So let's take closest approach. When Mars is at closest approach, it is winter in the north and summer in the south. The southern hemisphere is tipped towards the sun at closest approach, and it's tipped away from the sun at farthest approach. So out here, well, when you're at closest approach, you're going to have warm northern winters and warm southern summers. At farthest, you're going to have cool northern summers because the tilt is now, the northern hemisphere is now facing the sun, and cool southern winters. And so you're going to have different temperature variations in the north versus the south. The north will go from a warm winter to a cool summer, a smaller temperature variation. But in the southern hemisphere, you'll go from a warm summer to a cool winter. So a much bigger temperature variation in the south. And that will have impacts on weather changes. In fact, that large temperature change can sometimes kick up global dust storms that cover the whole planet. We'll get back to that later. Okay, so those are kind of the orbital properties and the bulk properties. Let's talk a little bit about the interior. And most of what we know about the interior, we just know from the density. Now, with Earth and with the moon, we have seismographs on the surface, all over the surface. We use that to get extra knowledge about the interior. Whenever there's an earthquake or a moonquake, we can watch those, watch what comes back up, to the surface and figure out what the inside was like. But with Mercury, we couldn't do that. We just had to rely on the density. Mars is kind of in between. The Viking landers back in the 70s did have some seismographic equipment that didn't work very well. Just 2 years ago, we landed a mission on Mars called InSight. It has a little drill. It's trying to drill a hole down into the dirt to study, what's underneath, but also has a seismograph. That's one of its primary missions. And that was activated in 2019. So we've had about 1 year worth of seismic data from Mars now. And there are indeed Mars quakes. They're rare and not very strong, but they're there. But we don't yet have enough of that to determine what the interior is like. So instead, we just have to go on the density. And the density, we said, was similar to the moon's density. So Mars's inside is probably something like this: a small metal core. There has to be some metals there to explain the density, and a large mantle. Except Mars is bigger than the moon. It's slightly bigger than Mercury. So imagine something slightly bigger than Mercury, but this division of rocks and metals. Okay. Now, the other thing, or another thing we know about the interior, we know from the magnetic field, or the lack thereof. There's a small, weak, piddly magnetic field, but approximately it's the same as no magnetic field. Now, Earth has a strong magnetic field because we have that conductive fluid layer, metal. There's metal in the core, fluid, and we're churning it up quickly, spinning quickly. Now, with the moon and Mercury and Venus, they're all rotating slowly, and consequently, we did not have a magnetic field, and not a strong one. Mars is rotating quickly. It's rotating once a day, same as us. but it does not have a strong magnetic field. It has a metal core. So what's that tell you about that metal core? Rapid rotation, metal core, no field means
It's not fluid.
it's not fluid. At least it probably isn't. I mean, we can't go down, drill down and check or anything, but if it was fluid, given the rapid rotation, it'd probably have a strong magnetic field. So it's probably not fluid. And that's actually not surprising because it's a small world. I've mentioned this before. Small worlds lose their heat quickly. And we'll study this more in the warm-up question next time. But they have more surface area compared to their volume. Same as a skinny person. A skinny person has a lot of surface area, but not as much interior volume. You lose your heat through your surface area. You retain it through your volume. The bigger the world, the easier it is to hold on to the heat. The smaller, the easier it is to lose it. And so Mars, being a small world, they form hot, but it probably lost its heat quickly. And when it did that, that means the interior, the metal core solidified. If it's cool in there, it won't be liquid metal, fluid metal, it will just be solid. So that matches. The fact that there's no magnetic field matches with it being a small world. And also it's far from the sun. Mercury's a small world, but it's close to the sun. So that keeps it a little bit warmer. But Mars is small and far from the primary source of heat in the solar system. There's another consequence of this being a small world and cooling down quickly, and that is differentiation will not be complete. So let me approach it from another angle. Looking at this picture here, the surface of Mars has a red tint to it. And if you ever look at Mars at night, particularly when it's close to us like it is now, you can go out in the early evening, look up and find the red bright point of light. That's Mars. The human eye is not very good at, as we talked about, seeing color with faint things. But right now, Mars is bright enough that you can see its color and it has a red tint. And that red is coming from iron mixed in with the rock in the mantle and the surface. And it's because it cooled down quickly. Being a small world, it cooled down quickly. And so it didn't have as much time to differentiate. It did differentiate some, but not fully. Even on Earth, so here's our biologically suggestive differentiation figure again. Even on Earth, we didn't differentiate fully. There's still some metals mixed in with the rocks up here on the surface, and that's good. Else we wouldn't have metals, and boy, civilization would be set back without that material to work with. So it's good that we didn't differentiate completely. Mars cooled off even more quickly, and so it had less time to differentiate, and it's more mixed. There are more rocks mixed in with the core, and more metals mixed in with the mantle, and most of those metals are iron, which combine with different things to give you a reddish tint. And that's what we're seeing. The red is the iron mixed in due to incomplete differentiation, due to small worlds cooling quickly. So it's interesting how some of these really esoteric details can be explained by the exact same underlying concepts that we're using from world to world. Again, here's a picture of the surface, and you see how red the rock is. Okay, so that's the interior. We can only say so much about it because there's only so much that we know. Let's talk about the surface next. All sorts of interesting surface features. So here we have an elevation map of Mars. We can see both sides, and the colors don't mean anything. Blue does not mean water. White does not mean snow-capped mountains. Just as they did this color scheme, blue is low elevation, white is high elevation, though it does map where water might have been in the past, at least approximately, but that's not the intent. It's just an elevation map. Here it is stretched out, like you see maps of the Earth, where the North Polar region is stretched across the top, and the South Polar region is stretched across the bottom, and we see all sorts of stuff. First thing I'll point your eye to is the lack of plates. And we saw this on Venus. And when we looked at the elevation map of Earth and the elevation map of Venus, the boundaries between the plates are really apparent on Earth, and they're just not so on Venus, and they're not so here. We don't see any obvious plate boundaries when we look at this elevation map. So no plate tectonics. And again, that makes sense. Small world, lots of heat, becomes geologically dead. Without that heat to make a fluid mantle, you're not going to have plates moving around. Okay, so no plate tectonics, but it's not completely geologically barren. We have a region over here. And it's interesting. It's concentrated in a single region, and we'll give a reason for that, called Tharsis. This is the Tharsis Bulge. And in this region only, for the most part, you have tons of volcanoes, 4 massive ones and hundreds of smaller ones. You have a rift valley, the size of the United States, just a place where the ground split open. So geological activity. It doesn't appear to be active now. Those are not active volcanoes, at least not since we've been watching them. But they probably were active until recently, at least recently on geological timescales. But we'll have to explain why it's just this region here. Now let's see here. Oh yeah, and then the biggest, most obvious difference is the north to the south. The north, you can see from the blue color, that's low elevation. Most of this is about 4 kilometers below the planetary average. And there are very few craters. And we learned just from the warm-up question, few craters means it's a new surface. It probably cratered like crazy, but something wiped it clean about 3 billion years ago. And then you have the southern highlands, typically 4 kilometers above the planetary average, and supercratered, dense, like the lunar highlands. So these areas got bombarded right from the beginning and never got refreshed, never got renewed. So let me write that down. The 2 primary regions are the southern highlands, and they date to about 4 billion years ago. Should probably use a G for giga-year, but I'll just use a B for billions of years ago. And then we have the northern lowlands. And from the sparseness of the cratering, it's about 3 billion years ago. They're about as cratered as the Maria on the moon are. So something wiped it clean 3 billion years ago. And how do we explain that? How does one half of the planet get wiped clean and the other one doesn't? Well, this may seem crazy, but again, we've seen lots of evidence for this. The formation of the moon was a big impact with Earth. The supermetallic Mercury was probably a big impact, shedding off the outer layers of the mantle. Even the slow reversed rotation of Venus might have been due to a big impact, though it could be explained other ways as well. With Mars, it's got to be very precise to do this. But if you had a big impact that just grazed the North Pole of the planet, didn't smack directly into it, in that case, you either shatter the world like possibly happened with Mercury. Even if you don't, the energy melts the entire surface. But if you just graze the top, you would knock some material off of the northern hemisphere, which accounts for its lower elevation. You've removed some material, so it's deeper down. And that would melt just the northern hemisphere. We've built this in computers and tried it. And yeah, you can melt just the northern hemisphere with this kind of glancing blow. So that's what we think happened about 3 billion years ago. Had a big glancing impact. And this figure's from Mercury. We saw this before. This is the Caloris Basin, the Caloris impact on Mercury. It was a late hit, made the biggest crater on Mercury. And if we were saying bigger, it would have split the planet again, but it didn't. But it sent these seismic waves through the planet that focused on the opposite side, making an uplifted, jumbled, weird terrain. And that's what we think Tharsis is. We think something hit the planet, knocked off a layer of the upper atmosphere, melted, or the upper surface, melted it, and the shock waves funneled through the planet to this region here, lifting it up and making it geologically active again. It started out geologically active, the planet, and then cooled, and then was dead for probably about 1 billion years. And then you had this impact, and at least this region came to life again. Water came to life across the planet too, as we'll see. And then it cooled down again and became geologically dead. Let's take a look at Tharsis. So Tharsis is interesting. Again, it's a region that was lifted up. There's a lot of pressure underneath, a lot of heat. So it was active for a while. You ended up with some, the Ballast Marineris, which is this giant rift valley. Come back to that in a second. But also volcanoes. We spin around the volcanoes. There are 3 large ones and 1 really large one. So 4 big ones. The biggest one is Olympus Mons. It's the biggest mountain in the solar system. And then you actually have hundreds of small ones around here. The blue is fog, not water fog, but carbon dioxide fog. It gets cool enough in the mornings and the evenings that you get fog, and it kind of collects in the craters and around the volcanoes. So here's Olympus Mons, and it is big. It's 25 kilometers. Let me put up the dot cam here. Maybe the space here will be for Olympus Mons. It's 25 kilometers high by about 700 kilometers wide. It's about the extent of it is like the size of Texas. But the height is really high. It's a shield volcano. We talked about those. It's when you have a weak spot in the crust. The magma comes up and it pokes through and starts piling up a mountain. And the mountain can only grow so high. It gets so heavy and the rock can only hold so much weight. So then it starts to crumble out the sides and gets wider and wider and wider once you hit that maximum height. And the maximum height will vary from world to world. On like the Earth or Venus, you can get up to about 10 kilometers in height before the rock starts to crumble. Now, weight depends not just on the mass, but on the gravitational field. And we know that the surface gravity of Mars is 38%. We just looked at that. Let's round it off to 0.4. So if the surface gravity is only 0.4, that means we can build the mountain higher before it's holding the same weight. So how high? That's 1 divided by 0.4, which is 2.5. So on Mars, you can make the shield volcanoes about 2.5 times higher than you can on Earth or Venus. And 2.5 times 10 is 25. It explains the height of Olympus Mons. It's nifty how you can explain these small esoteric details with the same basic underlying concepts over and over again.
Does
That's
that
a
mean
little-
Mount Everest will like reach 10 and then just not grow?
So Everest is a little different. It's not a shield. It's not a volcano. It's a mountain. And it's being lifted up not just by, its weight, but you have 2 plates coming together and pushing upwards. So you have that momentum creating kind of a base, and it sits on top of that. So it's even higher. It's like 20-something kilometers tall. But it's not just its own weight, it's getting pushed from underneath. So that's why it gets to be taller. Good question. And this is an elevation, it's same thing. It's just an elevation map recreated on a computer. You can see the caldera, the opening. There's some impacts around here as well. And then let's take a look at Ballast Marineris. This is also in the Tharsis region. It's a rift valley. Again, the pressure piled up underneath, raising the ground. And then when that pressure dissipates, the ground cracks open. It's a rift valley. We have them here on Earth, the famous one in Africa and in other places as well, but not caused by erosion, not wind, not water, just the cracking of the Earth due to pressure underneath. Here's the Grand Canyon for scale. So this one is huge. It's like the size of the United States. And I have a little fly-through movie that's kind of fun, so I'll play it. Here it is. I'll play it at high speed since we're running short on time. So this is based on elevation data with some artistic license taken on top of the data. But we're flying along an area the length of the US. Then just it shoots us up into orbit so we can see the full extent of it. And the final surface feature is this right here. It's called Hellas Basin, and it's just a big impact, but it's been heavily cratered. So this happened early on. Hellas Basin was about 4 billion years ago. Now I'll add this under the surface features. Hellas, about 4 billion years ago, hit in the southern highlands and then just kept getting cratered on top of it. So those are your primary features. This map shows you where some of the things have landed: Viking 1, Viking 2, Pathfinder, Opportunity, Spirit, and Curiosity is down here somewhere as well, I believe. Now let me just get us started on water. I may go a couple minutes over just to stay lined up with the other class. So evidence for water on Mars, we'll just start this here. Lots of different lines of evidence. Here in the southern highlands, we see riverbeds telling us 4 billion years ago, water was flowing, and we can date that from the craters again. Here's another example. This is a river, an empty riverbed on Mars. Shows us that water is flowing here at some point. This is the Red River on Earth. Notice how rivers meander and curve like this. There's a science to that. How it curves depends upon the fluid flowing through it and the force of gravity. And the meandering here is consistent with water, but under 38% gravity. And then the water disappeared. So water was flowing around initially 4 billion years ago, and then the planet cooled off, all that froze, went under the surface and into the poles. But then 3 billion years ago, when we likely had that smack creating tharsis that delivered a lot of energy to the whole planet, melted the water. And so we had a renewed period of water on the surface about 3 billion years ago. Flash floods, you can see how they kind of worked their way around the craters. These would have been islands long ago in some large river. Giant delta systems where the water is pouring out of the southern highlands into the northern lowlands. If we zoom into this crater, it's just one example called Holden Crater. These would have been lakes. Water would have flowed in and pooled there. And you can see here kind of an upper region. This would have been beachfront property on Mars about 3 billion years ago. The crater would have filled with the lake, and this would have been the beachhead. We also have other evidence of water all across the northern lowlands. These little, they're called blueberries. They're about the size of a blueberry. They're smooth, and they're formed here on Earth too. You get it when you have standing water. It can't just be running water. The water has to stand. It has to be underwater for long, long periods of time, like stream beds and lake beds. You can find these. They're carved. It's a type of erosion, leaves a smooth little bead. And this suggests that there is water all in those northern lowlands. They're already a low elevation. The water runs into them. You could have an ocean the size of the planet. Now, we don't know if the whole thing was filled up or if it was filled up permanently or if it would come and go, but there does appear to have been standing water in the northern lowlands. I'll just show you 2 more slides to keep up with the other class. You know, Mars cooled down again, small world. It got a little extra energy from that impact, but then it lost it. And so the water froze again, went underground. We now have spacecraft that orbit the planet and can, using radar technology, can penetrate into the ground and find the water. And it's under there in the form of permafrost in different areas, but most of it's concentrated in the polar caps. It's not all water in the polar caps. There's a lot of frozen carbon dioxide, as we'll learn, but there's water, especially in the northern cap where that ocean likely was. So it makes sense there'd be a lot of water there. And just another piece of evidence that there's water under the surface. On the left, you see a crater caused by an impact on the moon. And you see the ejecta blanket, and it looks like dry dirt was thrown out. But on the right, we have Mars. And it looks not dry. It looks like mud slopped out. So it impacted, deposited a lot of energy, melted the permafrost, mixing with the dirt, making mud, and threw mud out. So again, we think there's a lot of water there. Next time, I'll show you some of the best evidence, and I'll also do a demo where I'll boil some water and pour it on my hand. And so that will encourage you to all show up next time. So I didn't have time to do that today, but that's coming up next. Okay, that's it for today. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
My pleasure.
Thank you.
I have a question about a specific exam question.
Yeah, go
Although I
ahead.
wasn't sure if I should save that for office hours tomorrow or now.
That's okay. Now's
Okay.
fine.
Let me get the exact number. It was a question that I got wrong, and I think I know why I got it wrong, but I would like confirmation that
Sure.
that's why I got it wrong. So it was question 15, the one that talked about the moon measured to have a density of 1,000 kilograms per cubic meter. And in doing that one, I was stuck between the answers of gas and ice because I remembered in the notes writing that water, ice, and compressed gas were all 1,000.
Yep.
I guessed gas and I was wrong. So was the answer ice?
It was ice, and it's
Okay.
because it's a moon. To compress the gas, you need to have like a gas giant. If it's a moon, it's not going to be made out of gas. It's going to be
Right.
ice and rock.
In retrospect, that makes sense. All right. Thank you.
Sure. Anything else? No. Okay.